Okay, let's talk about sequences. So this is a very interesting topic. And the best part about this is you can make your own stuff up very easily. So let's say I gave you the numbers 2, 4, 6, 8, 10. Like, you recognize these as even numbers, right? And like, this is a sequence, like, because it comes one after another, like the numbers come one after another, and these are just even numbers. So we know these are even numbers. Even numbers. Well, what if I asked you, what's the 50th even number? Well, you would just tell me 2 times 50 is 100. So the 50th even number is 100. But how would you write that more formally? So what you can do is 2 times, let's use n, because n is usually used for sequences. So let's say you gave this sequence as sequence s is equal to 2 times n, where n is equal to 1, 2, 3, 4. These are just normal numbers, right? Until infinity. These are the numbers. So if I ask you for the 50th number in this sequence, so let's call even numbers a sequence. If I ask you the 50th number, you just put 50 in place of n. So you tell me it's 2 times 50, which is equal to 100. And that is the 50th even number, and we know that is 50th even number. If I asked you the 4th number in this sequence, that would be, so this is number 1, number 2, number 3, number 4. The 4th number is just 8, you can see it right there. If you did 2 times 4, you'd also end up getting 8. We saw even numbers, let's do odd numbers. So odd numbers are 1, 3, 5, 7, 9, so on and so forth, right? And I'll tell you, this sequence, let's call it S, is equal to 2n minus 1. I'll tell you that right now. So if I ask you for the 50th odd number, you tell me, well, it's 2 times 50 minus 1, which is 99. So that's the 50th number in the sequence. I'll tell you how to get to the 2n minus 1 later, but you have to understand like how useful this really is. So what if I gave you the sequence like 4, 8, 25, 31, and I told you the formula is equal to whatever you want. You can choose your own formula. If I asked you for the 95th number in that sequence, well, you can just put 95 in place of n in that formula, and you'll end up getting the 95th number in that sequence instead of writing it all down. Because over here I can tell you 1, 3, 5, 7, 9. You will tell me 11 and 13 come next. You already know what comes next. But here you don't know what comes next because you've never seen this before. I just made that up. It might not even have a formula that works. But once I give you the formula that if it does work, you can tell me the 95th number without calculating all the 94 numbers before it. So now, how do we actually get the formula for the sequence? Well, 2n is very easy. 2n minus 1 is still easy. But if I gave you the sequence, let's say I gave you 4, 8. No, let's not start with 4. Let's start with 6. I gave you 6, 10, 14, 18, and so on and so forth. Well, you can still see if you add 4 to 6, you get 10. If you add 4 to 10, you get 14. If you add 4 to 14, you get 18. So you can tell me, well, the next number is going to be 22, and then it's going to be 26. But again, if I asked you for the 90th number in the sequence, well, you don't want to calculate all the 89 numbers that come before it. So what you can do is you can find the formula for the sequence. So you write S is equal to, and now we're going to have a formula for the sequence. So a sequence where the common difference, so the common difference here is plus 4, right? Because you add 4, you add 4, you add 4. So these are called linear sequences because their common first difference, well, what all that means really is that this is the difference, this is the difference, this is the difference, and they're all the same. They're all plus 4. So the common first difference in our case is just 4. So these are called linear because the formula will now be given in terms of 4 times n plus something. Let's just call it k for now. We need to find what k is. And the way you get k is, well, you have the numbers 6, 10, 14, and 18. And now, this is the first number, this is the second number, this is the third number, this is the fourth number in the sequence. We didn't get any more, we just got the first 4. So what we do is, we do 4 times the first number, so that's 4. And then 4 times the second number is 8, 4 times 2 is 8, 4 times 3 is 12, and 4 times 4 is 16. So we're assuming that our sequence is just 4n. That's what we're assuming. And if you assume our sequence is just 4n, then we end up getting 4, 8, 12, 16. Because you can say the next step is going to be 20 and 24. But that is not our sequence. Our sequence is actually 6, 10, 14, 18, which is similar to 4n, but it's not the exact same. So to find k, what you do is, let's draw some lines here. So all we've done so far is we've written the numbers out in the sequence, and we've written 4n out. That's another sequence. We've made our own sequence, and we've written that out underneath it. And we got 4 because we know that's the common first difference. The difference here is plus 4, plus 4, plus 4. It could be negative as well, but as long as they're all the same difference, then you can have your own sequence right here in terms of that number. So now we do 6 minus 4, and you get 2. Okay. We do 10 minus 8, and we get 2 again. We do 14 minus 12, and we get 2 again. And we do 18 minus 16, and we get 2 again. So you can see now, this other sequence, if we had a sequence 2, 2, 2, and 2, well, if I asked for the 90th term in this sequence, you'd still tell me 2, most likely, right? Because this sequence, literally, s is equal to 2. This is just a constant. You're saying that the sequence is just the number 2 infinitely many times. Well, and it's positive 2, right? Because it's positive 2, positive 2, positive 2, positive 2. Well, what you're saying is if you add the constant plus 2 to our original sequence, then we can end up getting the formula for the sequence right here, 6, 10, 14, 18. So I claim that if s is equal to 4n plus 2, then our sequence 6, 10, 14, 18 is valid. And let's try it. When n is equal to 1, you have 4 plus 2, which is 6. When n is equal to 2, you have 4 times 2, which is 8, plus 2, which is 10. N is equal to 3, you have 4 times 3, 12, plus 2, which is 14. N is equal to 4, you have 4 times 4, 16, plus 2, which is equal to 18. So it does work, and our sequence is correct. So if I ask for the 90th term now, you would just tell me, well, 4 times 90 plus 2, which is equal to 362. And now you don't need to calculate all the other terms. All you need to do is find the formula, and then you can put the number back in. And this does not take a lot of time because we recognize 4 from the beginning, and then we found out this is just a constant sequence right here. Now you may be thinking, well, are these the only type of sequences? What if I told you I could write sequence like this? I could say s is equal to 3 to the power n, and that becomes 3, 9, 27, 81, and so on and so forth. If I asked you for the 5th term, you'd say 3 to the power 5. I could write s is equal to 3 to the power n plus 2n plus 1. Well, that would become 3 plus 5 plus 1 is 6, the first term. Then you add 3 squared plus 4 plus 1, which is 14. And then you keep on going forever, and you can choose whatever term you want to calculate. But another one we'll focus on, that's important, are quadratic sequences. Of course, once you see linear, you just know quadratic is going to be there somewhere. Quadratic sequences. So, how do you get quadratic sequences? So let's say I told you s is equal to n squared plus 2n plus 1. Well, to calculate the first few terms, you would have 1 plus 2 plus 1 is 4. And I realized what I did here. I'll show you what I just did. So then you have 2 squared is 4, plus 2 times 2 is 4, plus 1 is 9. And then you have 3 squared plus 6 plus 1 is 16, and so on and so forth. And you will realize these are square numbers. This is actually 2 squared, this is 3 squared, this is 4 squared. This is all by accident, it worked out. Because if you factorize this, you end up getting n plus 1 all squared. So instead of when you put n equals 1 in this, you end up getting 2 squared, which is the first term. When you put n is equal to 2, you end up getting the second term, which is actually 3 squared. And then so on and so forth. But once again, let's say I gave you the sequence now, 4, 8, 14, 22, and it continues. So how would you find the formula for the sequence? Because once again, I want to find the 50th term in the sequence, for example. So first we need the formula, and then we'll be able to get the 50th term. Well, we know the first difference here is 4, but now the difference here is 6, and now the difference here is 8. Okay, that's annoying. So it's not a linear sequence. That's an 8 right there. That's an 8. So it's not a linear sequence. But now if you look at the sequence 4, 6, and 8, what do you notice? Well, this has a difference of 2, and this has a difference of 2 as well. 4 plus 2 is 6, and 6 plus 2 is 8. Well, plus 2, plus 2. So the second common difference now, remember here was the first common difference, common first difference, but now we have the common second difference. Second difference is equal to 2. So this becomes, since it's a second difference, it's going to be a quadratic sequence. When it was the first difference, it's a linear sequence. So now we have the common second difference is 2. So now we know it's a quadratic sequence. And I'll tell you this right now. What we do is, So you'll have n squared plus, let's say, kn plus d, for example, because we need to find k and d. Because it's a quadratic sequence, it will be in the form something squared plus something plus something. So if you have the common second difference of 2, what we do is we take this 2 and we divide it by 2. So we do 2 divided by 2, which is equal to 1. And if it was like the common difference was 4, for example, we do 4 divided by 2, and we end up getting 2. And then this becomes n squared, and this becomes 2 times n squared. It's a bit difficult to get your head around, but just know, whatever the common second difference is, you divide that by 2, and that's like your new sequence. So now, in our case, we have n squared as our new sequence. So let's write the original terms again. We had 4, 8, 14, and 22. And now if you use n squared, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. So now we have a new sequence. Well, we do what we did with the first one. We just subtract, 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 and subtract. 4 minus 1 is 3, 8 minus 4 is 4, 14 minus 9 is 5, 22 minus 16 is 6. Okay? These are not constants, these are different numbers, but now you realize if you wrote the sequence 3, 4, 5, and 6, well, the common difference here is 1, 1, and 1. So now this is actually a linear sequence. And remember what we did with the linear sequence right here. If the common first difference is 4, then we write it as 4n. Well, since the common difference is 1, we just write it as 1n. So now we have 1n plus, so instead of writing 1n, I'll just write n. So we have n plus something. That's going to be the formula for this sequence right here. Well, you have 3, 4, 5, and 6. And we'll do the same thing. So we have n. So we just have 1, 2, 3, and 4. This is the first term, second term, third term, and fourth term. Well, now you can see straight away that 3 minus 1 is 2, 4 minus 2 is 2, 5 minus 3 is 2, 6 minus 4 is 2. So now once again our constant is 2. So now this sequence 3, 4, 5, and 6 is given by n plus 2. This is the sequence n plus 2. But we don't care about this sequence, we care about this sequence right here. 4, 8, 14, and 22. And that's given by n squared plus kn plus d. Well, can you see what k and d are? K is just 1 right here. The coefficient of n is just 1. And d is just the plus 2 right there. Now we have n squared plus n plus 2. And that is actually our sequence. And we can see that it works. If you put n is equal to 1 in this, you get 1 plus 1 plus 2 is 4. You get n equals 2 in this, you get 2 squared 4 plus 2 6 plus 2 8. And you put n equals 3, you get 9 plus 12 plus 3 12 plus 2 is 14. And n equals 4, you get 16 plus 4 20 plus 2 22. So if I ask you for the 50th term, is that what I asked you for? Yeah. You would say 50 squared, which is 2,500, plus 50 plus 2, which is equal to 2,552. So you can see, for this sequence right here, you'd have to then do plus 10, and then plus 12, and then plus 14, and plus 16. Instead of doing all of that until the 50th term, you can just find the formula for this. You can find the formula that tells you what the nth term in the sequence will be, because this is like the nth term. This is n. This is the n plus 1 term. These are just like notation you have to get used to. This is the nth term, this is the n plus 1th term, and it just goes on forever. And then you have 50 over here, and then you have 65 here, and then you have whatever, right? N just means any term right here, and that term is given by, in this case, is given by the formula n squared plus n plus 2. You can put wherever you want in for n, and you end up getting the term that you want. And this all makes more sense once you do more practice. And in the question that we're going to do right here is another quadratic sequence, so we'll be able to have some more practice with those type of sequences. So the sequence of diagrams above is made up of small lines and dots. Complete the table. Okay, so we have, these are like half of squares. You can see 3 by 3, 4 by 4, 5 by 5. Okay. So the number of small lines in diagram 1 is 4. 1, 2, 3, 4. Diagram 2 it's 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 18, 28, whatever. The number of dots here is 4. This is 6, 2 is 8. This is 4, 12, 8, 11, 2 is 13. That's 19. And now we have to find diagram 5 and diagram 6. Okay. So how can we do this? Well, we don't need to find a formula first, because that's going to be in the next question right here. What we do now is we realize, okay, so this is 4 plus 6 gives us 10. plus 8 gives us 18, plus 10 gives us 28. Well, the first difference is not the same, but the second difference here is plus 2. And then now we have 8 plus 2 is 10. Well, what's 10 plus 2? That's 12. So if you add 12, you get 40. That's plus 2. And then what's 12 plus 2? Then that's 14. So plus 2 right there. What's 40 plus 14 is just 54. So that's going to be our diagram 6. You can see, since we only needed the first 6 terms, we can just calculate them by hand. But this is actually a quadratic sequence because remember, the second difference is the same. What about this right here? You have plus 4, plus 5, plus 6. Well, second difference is plus 1, plus 1. That's another quadratic sequence. But now here it will be plus 7 because the second common difference is 1. So 19 plus 7 is 26. And then plus 8. Because 7 plus 1 is 8. 26 plus 8 is 34. And so on and so forth. But now it says for diagram n, find an expression in terms of n for the number of small lines. Okay, so we're looking at this right here. We don't care about the number of dots right now. So how would we find the number of small lines? So we have the sequence 4, 10, 18, 28. So all this is saying is basically what we've been doing before in the previous question. Like, find a formula for this sequence, a number of small lines. So if I give you diagram 55, you can tell me straight away, okay, you will have these many small lines. We don't care about number of dots for now because it doesn't ask us that. So how do we do that? Well, first difference here is 6, 8, and then 10. Second difference is 2 and 2. So now we know it's a quadratic sequence because the second common difference is the same. And since the second difference is 2, we do 2 divided by 2 and you get 1. So you have n squared plus bn plus c. We have to find b and c basically. Well, once again, we write our sequence down. So we have 4, 10, 18, and 28. And since it's n squared, we do 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And then we subtract. And hopefully we get a linear sequence. Let's see, 4 minus 1 is 3, 10 minus 4 is 6, 18 minus 9 is 9. Okay, so this is good. Then 28 minus 16 is 12. So this is a linear sequence. We have 3, 6, 9, and 12. Well, what type of sequence is this? Well, I can tell you right now it's 3n, and it's pretty obvious to see, but let's do it the way we're used to doing. So the first common difference is 3, 3, and 3. And these are all the same. So we have 3n plus something. Let's call it m, for example, right? We have 3n plus m. We need to find what m is. Well, once again, what we do is we write a sequence down 3, 6, 9, and 12. And then we put 3n, we put n equals 1, 2, 3, and 4 for 3n right here. So we have 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. We subtract each term individually. So we get 3 minus 3 is 0, 6 minus 6 is 0, 0 and 0. So this becomes 3n plus 0, basically. We don't really care about this, we can get that out. So we have this sequence is 3n. We can compare right here. So our b is actually equal to 3. And our c is actually equal to 0. So we have n squared plus 3n plus 0, which is just n squared plus 3n. So I can write that as n squared plus 3n. That's our sequence. And we can see that it works. Let's choose, we did diagram 6, right? Let's see if we got the right answer. So for diagram 6, we would have 6 squared, which is 36, plus 3 times 6, which is 18, which is actually 54. So we would have 54 small lines. And we got that by just using, our logic. And now we can see using actual math that is the right answer. If you wanted diagram 7, we would do 49 plus 21, which would be 70. So that would have 70 small lines. And you now know what the value of that is. Well, we do it once again. Diagram R has 10,300 small lines. Find the value of R. Okay, now how would you do that? Well, R and N is the same thing. So we have R squared plus 3R. And now you're saying for some value of R right here, so question mark, you will actually end up getting 10,300 small lines. Well, this is just a quadratic equation, right? You have R squared plus 3R is equal to 10,300. Well, you can bring this to the other side. You have R squared plus 3R minus 10,300 is equal to 0. Okay, we're gonna use the formula for this. Okay, so r is equal to minus 3 plus or minus square root of 3 squared is 9 plus 4ac, so that's 41,200. This is gonna simplify to a nice number, don't worry. That's why it's only 2 points divided by 2. Well, r is equal to, let me use my calculator, 41,209 square root of that. It's 203. Okay, so r is equal to minus 3 plus or minus 203 divided by 2. So you get r is equal to either minus 3 minus 203 divided by 2. So it's either minus 103 or r is equal to minus 3 plus 203 divided by is equal to positive 100. Well, let's use our brain, right? You can't have a diagram negative 103. We don't, that's not a thing, because this is actually real life now. We're actually drawing stuff. You don't have negative diagrams, you only have positive diagrams. That means the only diagram that could work in this case is 100. So the 100th diagram would actually have 10,300 small lines. And you can put 100 into this right here, so you would have 100 squared plus 3 times 100, which is 10,300. And you could have just guessed 100 straight away. You probably did guess that, but I just wanted to use the formula just to make sure. And yeah, you get the same answer right here. So I hope that all makes sense. And yeah, like, any question about sequences, leave them in the comments. I hope you liked the video. If you did, then like, share, subscribe, and comment. It's not really that difficult, this topic. It's just, it takes a lot of practice and getting used to it. But that's everything in math. So yeah, do some practice on these questions, find some online, and it's actually pretty fun. Once you like get used to it, you can make your own questions up too. This is like a bonus section. So I mentioned in the thumbnail that we will be doing the Fibonacci sequence. This is a very famous sequence, but the way you get the sequence is very interesting. So the sequence goes like this. You have 1, 1, 2, 3, 5, 8, 13, 21, and then so on and so forth. And the way you get the next term is, so the first two terms are just given. So you have 1 and 1 given. Okay? You have that given. The third term is the second term plus the first term. So third term is equal to the second, t for term, plus the first term. The fourth term now is actually given as the third term plus the second term. So now you can see with sequences you can get very creative. You can do whatever you want. You could multiply it, but in this case we're just adding them. So you can see 8 is actually 5 plus 3. That's how you get 8. 13 is actually 8 plus 5. 21 is actually 13 plus 8. So once you're given the number 1 and 1, you can continue. So let's make our own Fibonacci sequence, right? Let's call it Maths with Musa sequence, because why not? Let's call it that. And how would you do that? Well, let's say we start with the numbers 3 and 4. Now we can make our own sequence. So the next term is going to be 3 plus 4, which is 7. Then after that, you would have 7 plus 4, which is 11. Then you would have 11 plus 7, which is 18. Then you have 18 plus 11, which is 29, and so on and so forth. Now, what's the interesting thing about this? You might be like, this is just a random sequence, we just made stuff up. Now, the interesting thing is, if you take the next term, so we have the nth term, and then we have the n plus 1 term, right? If you take the next term divided by the term before it, so let's say we did 4 divided by 3 in this case, right? We have 4 divided by 3. That's approximately 1.333, right? Recurring. Let's say we did 7 divided by 4. Well, that's approximately 1.75. That is 1.75 actually. That's equal to 1.75. Let's say we did 11 divided by 7. Well, you end up getting 1 point something, 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 right? You'd end up getting some decimal. In this case, 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is like 1.667. 8 divided by 5 is 1.6. 13 divided by 8 is 1 point something, 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 something. Now the interesting thing is, and this is why it's so famous, is because all these numbers, like look, here we made our own first two numbers up and then we continued the sequence. But these numbers here, as you get like bigger and bigger numbers and you can try yourself, they approach a value, and this has a special name. So we denote it by the Greek letter phi. And this is equal to 1.618, so on and so forth. Of course, this is also like never-ending decimal. This is like up there with the level of pi and other numbers as being very useful, because this is actually called the golden ratio. And the funny thing is, or the interesting thing is that it appears in so many things. It appears in like sunflower, it's like the way the sunflower petals are, the sunflower seeds are. It's like a lot of stuff in nature is very related to the golden ratio. Stuff in your body is related to the golden ratio. So like if you measure so let's try this experiment if you want. So measure the distance from your hip to your toe, or hip to the floor, and then measure the distance from the knee to the toe. And you will see that once you, so let's say you get this number as like number x, and you get this number as a number y, right? When you do x divided by y, it will actually be equal to 1 point something something something. And science has shown that the closer this number is to 1.618, which is the golden ratio, that's, I guess, the more scientifically perfect your body is. That's like the ratio that humans find, you know, appealing or attractive. And something on your face as well, like the distance between your eyes to your nose, and literally everywhere, even in Da Vinci's drawings. If you've seen the famous drawing, the Vitruvius Man, right? It's like a man, and he's like, I'm very bad at drawing, so I'm not even going to try to draw it. But it's a famous drawing by Da Vinci. I'll try to put it up on the side. You will see in that drawing, he uses the golden ratio as well to like get the measurements correct, because this actually occurs a lot in nature and in our bodies and everything. You can try these experiments. You can try actually from shoulder to fingertip, shoulder to finger. And you can also try from I think it's your elbow, from your elbow to your finger. And of course, no one's going to be exactly 1.618. And if you get 1.618, it doesn't mean you're perfect. But that is what like the ideal body measurements are. So you might end up getting like 1.4, for example. Here you might end up getting 1.7. And here you might end up getting like if you did this ratio divided by this ratio, you might end up getting something like 1.4. While at this ratio to this ratio, you might end up getting something like 1.7. Doesn't mean your body's not perfect. That just means that it just shows that 1.618 is there somewhere. And like, you don't have to believe it, but it approaches 1.618, especially in this sequence right here. Once you get higher and higher up, you can find proofs online. That's like very complicated, not for our level, but they do approach 1.618, and that's why it's called the golden ratio, because it's so common and it's so unique, like the way it came about. It came about when like this famous mathematician, his name was Leonardo Fibonacci. He was studying like how rabbits populate the environment. So like if you put one rabbit and then you put another rabbit, so that's 1 and 1, well, you get 2 rabbits, and then they will reproduce to give you 3 rabbits, and then these 3 will reproduce to give you 5 rabbits, and then those 5 will reproduce to give you 8 rabbits, and then so on and so forth. And well, that's the Fibonacci sequence. That's how it came about. And now you can see it has so many different applications in nature. So yeah, hope that's interesting to you.